All right, now we're recording. So, does anybody have any questions about anything, either on the subject of biology or just the way the course is working, anything like that?
No, I don't think I have any questions.
Okay. I will say I got an email question. It was a good question. They're asking when the exam is, and we don't know yet.
That was
Oh, there you go. Yeah, I don't know when the exam is yet. And as I told you, as a reminder, always check the syllabus for the tentative schedule at the back or the bottom of the document. The thing about that is, if I remember correctly, since we are in week 3, technically, according to the syllabus, this is the exam week. But obviously, we're not there yet. The one thing that will never change, knock on wood, I can't see why it would, it never has, is it's always going to be 3 chapters and then an exam. So, right now we're in the middle of chapter 2. So we know at the very least we still have to finish chapter 2 and then get through chapter 3 before we can have the first exam. So you'll always know, or at least that, based on the exam or where we are in the chapters, you can have a decent idea of when the exam is. So there you go. Good morning, Boyd.
Good morning.
So yeah, that's the thing about the exam. Specifically, we don't know when it is. And right now, since we're still in the middle of chapter 2, I really don't even have a good estimation yet. I would assume we can finish up chapter 2 today, which means we might be able to knock out chapter 3 maybe this week or maybe on Monday. And I'm really just guessing here. So that means maybe we'll have the exam sometime next week. But again, we'll know a little bit more once we get through chapter 2 and kind of get into chapter 3. Good morning, Hamrick.
Good morning.
But yeah, that's the thing about the exam. What else can I say? Oh yeah, I mean, I'm sure you guys know by now, but just as a reminder regarding the exams, one of the best ways to study for it is to do those study guides, because again, those are the questions I use to write the exams. I take those questions, I reword them, and that's what you'll mostly see on the exam. Another thing is, if you're doing the exam online, as far as the format's concerned, it's just like the study guide. So you'll get used to going in there and scrolling through and, selecting from the multiple choice and hitting the submit button. Those are all things that you would, it would be good to get practice with. So yeah, do those study guides. It's good to help you for the exam. You get a little bit of independent work points for it. And that's it. And other than that, the only other thing that's going to be on the exam is a little bit of information from the syllabus. So as I've been saying from day one, read your syllabus. Anyway, good morning, Chloe. Good morning, Schmidt. Let's see here. Chloe and Schmidt. All right. Speaking of independent work, good morning, Simpson. And good morning, Julia. Let me write that down. 1 second, please. Simpson. Julia. Okay. Anyway, as I was saying, since I'm recording, I'm just giving some announcements before class. That way you guys can refer back to them if you want. We don't have to waste lecture time talking about announcements. Independent work, the first week is over. So by now you should have had that second form that's been shared with you on Google Classroom. So for this week, you'll write stuff on that one. And how the points work is, you needed to have 7.2 points by today for an A. And if you don't, then you just have a lower grade. But the good news is you can just make up for that next week. So by the end of this coming week, like from a week from today, you should have 14.4 points. So, if you don't have the points you need this week, as long as you have 14.4 points next week, then you're back at an A. So that's the good thing about independent work. It's flexible in that way. Anyway, it's 8 o'clock. I'm going to go ahead and take attendance. I know that might seem weird because you're still going to need to send me the keywords for attendance, but I like to know, at least mark down who's here at the beginning and who's here at the end. So anyway, if you hear your name, let me know. Let's see. I know Julie is here. I saw Smalls come in. Knox. Is Knox here? All right. I know Larissa is here. Is Buckley here? Okay. I know Hamrick is here. Is Harvey here? All right. Thompson? Page? Brett? Torres?
Here.
Good. Thank you. I need to see that. I know that Schmidt is here. Breeden? Robinson? Vance? White?
I'm here.
White?
Yeah, I'm here.
All right, thanks. I know Simpson's here. I know Cordone is here. Valencia? I saw Davis come in. I know Reedy's here.
Here.
Bunch? All right, great. Reed is here. McDay was here. McDay, are you here? Nah, I need to watch the video. Okay, and I know Boyd's here. Did I miss anybody? Okay, so I'm just going to jump right into chapter 2. Who was it? I'm sorry. Bunch. No, I got you. You're good. But thank you. All right, so.
Did you get me?
Nope. Thank you. Wait. No, I did not. Got your cousin. Okay. So I think everybody's accounted for. Let's go ahead and get started with chapter 2. Hopefully we can finish it today. There we go. Yeah, here we go. Yeah, we need to hurry up. I need to hurry up. I'm going to get through this quickly. Obviously, if you guys need me to slow down, let me know. The first word for attendance is going to be the word maybe. Like, I'm maybe able to go back to class next week, assuming my son is the last person in the house that has COVID and, he's free of COVID this week. Anyway, first word is maybe. Let me fix this. On the wrong side. So while I'm pulling this up, getting us to the correct side, can someone please confirm that you can see my PowerPoints and you can see me scrolling around in there?
Yeah.
All right.
I
Okay,
can.
perfect. So here we go. Last thing we talked about was the atomic mass. Not the last thing, but close to the last thing. And remember, the atomic mass is the number of protons plus the number of neutrons. And you need to use that information in the exam. There'll be some questions where either you're given the atomic mass, or you're given the number of protons, or you're given the number of neutrons. And there'll be some basic math question where you have to figure something out. So if I give you the number of protons and neutrons, you just add it together to give you the atomic mass. Or if you get the atomic mass and the number of protons, then you just need to know protons plus neutrons gives you the atomic mass. And I will talk about it more, but I already did that in the last video. So here we go. Isotopes. So this is a good time to remind you where we left off. I told you when we're talking about atoms and elements, that is the number of protons that defines the element, right? So, for example, hydrogen always has one proton. If you add another proton to it and you have two protons, that is then helium. If you add another proton to it, that's then lithium, so on and so forth. You don't need to memorize that. The point, what you do need to know is that the number of protons defines the element. If you change the number of protons, then you change the element. So we've got that out of the way. And again, the last thing we talked about was the structure of atoms, and we talked about the atomic mass. And I used an analogy of fingers, right? I said how many humans have an average of how many fingers, and people said, I think someone answered 10, because you would think, right? Because when you look at most humans, they have 10 fingers. However, some humans have more than 10 fingers. Some humans have fewer than 10 fingers. So probably when you would say the average number of fingers for a human is probably, I don't know, like 10.001 or something like that. Point being, if you take an average, then you don't get the whole normal number. And that's the same with the atomic mass remember we talked about hydrogen, for example. The number was 1.008. So anyway, that brings us to, finally, isotopes. And you need to know what an isotope is. It's an alternate mass form of an element More importantly, here's the important part as far as the exam is concerned. It has the same number of protons and electrons. In other words, it has a different number of neutrons. So that's what you need to know. Again, if you change the number of protons, you completely change the element. Now we're telling you what happens if you change the number of neutrons. If you change the number of neutrons, you have an isotope. And I've already given you some examples. I just didn't call them isotopes. The last thing I showed you was 3 different versions of hydrogen. One of them had no neutrons, one had 2 neutrons, one had 3 neutrons, but those were all still isotopes of hydrogen. And here the example, this is not from your book, but the example is carbon. So carbon-12 is the most common. Not that you need to know that, it's just an example. It's called carbon-12 because that's its mass, right? 6 plus 6 is 12. Carbon-13 has an extra proton because 6 plus 7 is 13. Carbon-14 has 2 extra protons because 6 plus 8 is 14. Again, this is just an example. You don't need to know anything about carbon-13, carbon-12, carbon-14, none of that. The important thing here is that you realize these proton numbers didn't change and these electron numbers didn't change. Again, if you change the number of neutrons, then you have an isotope. That's what you need to know for the exam. Any questions about that? All right, here we go. This kind of goes back to what I was saying earlier about, I mean, that's a fake, I'm pretty sure that's a Photoshop picture. But again, there are some people with extra fingers. So again, the average human, or the humans on average probably have 10 point something fingers, right? And that, going back to carbon, again, there is no one carbon. If you were to look at every single carbon in the universe and study each one individually, you will never find one that's mass is 12.001 because it's going to be a whole number. It's either going to be 12, 13, or 14. So what happens is you add all those up and then you average it. So the fact that carbon's number is 12.011, right? That's really close to 12. So that can tell you, just by looking at this number, that almost all the carbon in the universe is this one, right? Because the number is very close to that. There's probably very few of this one and very few of the 14. And again, that's just an example. You don't need to know anything about the different isotopes of carbon or the exact number. I just want you to understand why that number looks the way it does, and I want you to understand about isotopes. Any questions? All right. So if someone's not on mute, it's not bothering me, but I just want to let you be aware, because if you're like me and you're at home, you might have some noises in the background, and for you, you might not want those noises recorded. I don't know. Anyway, since we're talking about isotopes, your book also talks about radioactive isotopes. So you already know what an isotope is. Excuse me. A radioactive isotope is just one that's radioactive. And what do we mean by radioactive? I mean that the nucleus decays spontaneously, as in, you know, the parts of the nucleus, which you do need to know. Remember, that's the protons and the neutrons. When we say it's decaying spontaneously, what we mean is it's losing those, right? It's losing protons, it's losing neutrons. Energy is coming out as well. And that's what we call radiation. Now, I'm going to put a big old X through this slide just because, as a reminder, anybody who's watching this or here live, this will not be on the exam. I'm not going to ask you anything about radioactive isotopes. But yeah, so now you know what it is. You kind of know what radiation is, some natural sources of radiation. You know, it's not always X-rays and nuclear bombs. There are natural sources. Radon is a gas that you can find. A lot of times in buildings, sometimes you have to test for it. You can look into that if you want. Anyway, any questions about this slide, which again will not be on the exam? All right. I'll remind you from chapter 1. Every chapter we do has this little section called the process of science, as you can see up top. And every time I'm going to skip it because this will never be on the exam. The process of science stuff won't. And it might be on the study guide. So if you need help with it, let me know. But as far as the exam is concerned, you don't need to worry about it. I do recommend reading it and thinking about it. Like I said last time, it's a great mental exercise to think about things scientifically. Anyway, let's get into this next bullet point. Let's talk about chemical bonding in molecules. Historically, I think this is the part where I won't say it gets harder, but I think based on conversations I've had and papers I've graded and exams that I've graded, I think these are the harder things, the harder concepts of the chapter. So keep that in mind as we move forward. Okay. As far as we're concerned in this class, if we're talking about chemical reactions, it's all about the electrons. And if you've done the pre-lab, which was due for chapter 2, lab 2, which was due last night, if you've done that, you're already kind of familiar with this because that last question asks, all right, well, this thing has 8 electrons or 10 electrons. Is it reactive or not? And that's what it's all about. The most simple thing to say, and this isn't 100% true, but as far as this class is concerned, it is. The most simple thing to say about chemical reactions and electrons is this. Atoms want to have a full outer shell of electrons. That's it. They'll do what they need to do to get a full outer shell. They'll give up electrons. They'll take electrons. They'll share electrons. Whatever it is, they'll do what they need to do to get a full outer shell. Also, on that note, if the shell is full, it's not going to be reactive. It's happy, so to speak. They don't obviously have emotions. They're not really happy, but yeah. So anyway, again, it's the electrons that are directly involved in chemical reactions. And again, if you were to really look into chemistry, that's not a 100% accurate statement, but as far as we're concerned in this course, that is. Like I said, it's the number of electrons that determines the chemical properties because basically it's just trying to get a full outer ring. Now, the inner ring is interesting because it holds 2 electrons. So if I were to draw, for example, let's see, something with 2 protons, and then here's the first ring, and it holds 2 electrons. There we go. And that's it. The first one only holds 2. Now this thing, it does have a full outer ring. Now you might be thinking, wait a minute, it only has 1. That's only the inner ring. Yes, and this is where it gets a little bit tricky for people. But sometimes the one ring is the only ring there is. So for some atoms, that first ring is the outer ring, right? So this one has 2 protons. That's a full outer ring. Oh, by the way, that's helium because it has 2 protons. So I'll draw this one for an example. It has 1 proton, therefore only has 1 electron. Now in this case, what we have here is hydrogen because 1 proton. And again, this thing needs to be full. And again, the inner shell is supposed to hold 2. This one only has 1. Therefore, it needs 1 more electron to be satisfied. So therefore, and again, this is hydrogen. Hydrogen is reactive. And hydrogen, again, as far as we're concerned in this class, always bonds once. Hydrogen only bonds 1 time because it only needs that 1 extra electron. Does that make sense, everybody, so far? Hopefully you're with me. Just keep in mind that atoms are always trying to fill their outermost ring. Sometimes that inner ring is the outermost ring. But yeah, so the first ring holds 2. Here, I'll change that 2 to a 3 here. I'll make this beryllium. Now, here we go. This one has 2 electrons on the inside and then only 1 on the outside. So this thing needs 7 more electrons to get a full outer ring. And this is just an example, so you don't have to memorize the exact this exact example. But again, this one wants a full outer ring and only has 1 when it needs 8. So it needs 7 more. So yes, technically it could get 7 electrons, but most likely the easiest thing to do would be just get rid of that electron. But again, what you need to know for the exam, it's the electrons that we're concerned with as far as chemical reactions are concerned. Atoms are always looking to fill up their outermost ring. The inner ring holds 2. As far as we are concerned in this class, everything else holds 8. That's not exactly true, but everything that we deal with, it will be 2 and then 8 and then 8. And usually we don't even deal with a third. Usually we don't even deal with a third ring, but sometimes we do. And again, for us, this is the rule. 2 on the inside, 8 on everything else. And again, if you were to look this up, it is slightly different when you get into so-called real chemistry. But for our purposes, this is the rule. So any questions so far? Okay, again, the purpose here is to get that full outer ring. Therefore, when atoms do this, when they give up electrons or they take electrons or they share electrons, that brings them together. And that is what a chemical bond is, right? It's all about those reactions. They're giving electrons or taking electrons and sharing electrons with some other neighboring atom. And because of that, they are now bonded. And there's different types of bonds, and that's what we're going to learn about. So any questions so far? Most likely, I'm not going to ask you the definition of a chemical bond in the exam. The next word for attendance is pirate, like, Pirates of the Caribbean. Okay, let's talk about the 3 different types of bonds. The first one we're going to talk about is an ionic bond. And that is when an atom loses or gains an electron and becomes electronically charged. Again, I'm going to use this one since I just did it. We got 3 protons here in the middle. Obviously, there's probably 3 neutrons too, but whatever. I'm just simplifying this to make things easier. So beryllium has the 3 protons. Therefore, because it has 3 protons and I haven't said anything about it having a charge, that means it has the same number of electrons. I'll draw this again. There we go. So there's beryllium with its 3 electrons that match its 3 protons. And again, this thing needs 7 more electrons to have a full outer ring. So, like I said earlier, it could, I guess technically it could get 7 electrons, but that would be quite the task. So instead, it's going to give up an electron, which means this thing that used to have 3 protons and 3 electrons is given up an electron, and it is now turned into something, obviously still has 3 protons, otherwise it would be a different element, but now it only has 2 electrons. And hopefully you remember from the pre-lab, what happens here? You've given up an electron. So now you have 3 plus things and you only have 2 negative things. So now this thing has a charge, right? It gave up an electron and it has a charge. Specifically, it has a positive charge, right? Because there's more P's than there are, or excuse me, there's more pluses than there are negatives. So what we have done here is we've created an ion because it gave up an electron. It is now charged. The opposite of this, and I'll just show you a picture instead of drawing it on the next slide, I'll show you a picture. Sometimes you could gain an electron instead of giving one up, but you're still going to be charged. In that case, instead of having a positive charge, you're going to have a negative charge because you've gained something negative. The point here is when you're giving up electrons and you're taking electrons, that charge, that gives it a charge. And what do we call something with a charge? We call it an ion, and you need to know that for the exam. And at this point now, we've covered all the bases. If you change the number of protons, you change the element. If you change the number of neutrons, you have an isotope. And now finally, if you change the number of electrons, you make an ion. So yeah, pretty simple stuff. Again, you give up an electron, you take an electron, whatever the case may be, you are now electrically charged. And what happens when you have something charged next to each other? I have a plus and a negative next to each other. Can anybody tell me what would happen if that happened? Even if it was a magnet. Whoops. 2 magnets. There we go. I got awesome drawing skills. What would happen to these 2 magnets? I mean, I've shown it in the picture. You guys must be asleep. They attract each other, right? Positive and negative things attract each other, and that is an ionic bond. It's a bond between positively charged ions, oppositely charged ions, right? The positives and the negatives. And therefore, compounds that are held together by ionic bonds, those are called ionic compounds. So a long time ago, last week, we talked about what a compound was, right? It's like when you have 2 or more atoms together in a fixed ratio. Basically, you either have atoms, which is just the single element, right? The one atom, and anytime you bring them together, then you have a compound. So under that category, that big blanket statement or that blanket category of compounds, there's different types of compounds. And this is the first one you've learned about, an ionic compound. So it's specifically when you bring ions together. What else to say here? Okay, one last thing before I move forward. I will point out, so I've given this example where this thing gave up 1 electron and it had as a -1 charge. I think the next slide I'm going to show you, again, will show something with a -1 charge and a +1 charge. I just want to say for your own knowledge, not that you need to know this for the exam or the course, but it's not always like that. Sometimes ions have a -2 charge or a +3 charge. So it's not always just ones. I just wanted to point that out. Any questions about this slide? Here's a picture that's actually from your book. And again, when we first talked about compounds, this was one of the examples. The examples were water and salt, I believe were the only compounds that were the examples. But anyway, here we have sodium. You can see on its outermost ring, it only has the 1 electron. But remember, it needs 8, right? And 8 total, which means it needs 7 more, right? 1 + 8 is 7. Meanwhile, you have this chlorine, 1, 2, 3, 4, 5, 6, 7. This thing has 7 electrons on the outside. And remember, it needs a total of 8. Therefore, it needs to gain 1. So what's the easiest thing to do? Well, instead of this sodium getting 7 electrons, it's like, all right, let me just give up this electron to you since you need 1 and I need to get rid of 1. And then boom, sodium is now positively charged because it gave up an electron, and an electron is negative. Chlorine is now negatively charged because it gained an electron. And what happens again when you have a negative and a positive thing together? They attract each other. So you do not need to know this specific example of how sodium chloride works, but you do need to know, for example, that, well, this is an ionic bond. So if you get anything that looks like this, any equation that you see on the study guide or the exam that has a plus or a minus, you should know that we're dealing with ions. Therefore, it's an ionic bond. Yeah, I guess that's it. Yeah. Any questions about ionic bonds? All right. Let's move forward. If you download the PowerPoint, you can click on this little video and watch this animation. It's everything I just showed you, except it's animated. Excuse me. All right. So that's it for ionic bonds. Let us talk about covalent bonds. Now, in my opinion, these next two are the more important ones. Ionic, it's important, but as far as the semester is concerned, we're mostly going to be coming back to high covalent bonds and hydrogen bonds. So as far as the semester is concerned, these two that we're about to talk about are more important. All right. So can anybody tell me, I don't remember if I've said this, and I think it's in your book, but we keep talking about inner rings and outer rings. So like, for example, there's an inner ring, here's an outer ring. What is that outermost ring called? Does anybody know what that's called? For 1 point of independent work.
The valence shell.
Yes, good. Who was that?
Mason Hammer.
All right, awesome. Well, when you send me your attendance stuff, remind me that you also got that extra credit point. But yes, it's called the valence shell. So the outermost, or the valence ring, whatever you want to call it, the outermost ring, the outermost shell is called this is so horrible. I need a better apparatus. Valence shell. Okay. That being said, let's look at this word, covalent bonds. Co and then valent, right? So what do you think this bond might be involved with? So we know that an ionic bond is you give up electrons or take electrons. What do you think a covalent bond might be, based on the word and based on the fact that you know it's not what an ionic bond is? Any guesses? All right, let me ask you this. If I said to you, I have a college-age daughter. Now, if I were to say my daughter is cohabitating with her friend, what does that mean? She's cohabitating with her friend. What am I saying? No guesses?
Interacting.
I like that. Close. I mean, I'm sure they would interact, so I don't think you're not necessarily wrong.
Staying with each other?
Yeah, they live with each other. More specifically, they're sharing a habitat, right? Cohabitating. They're sharing a place to live. Back when she was a kid, I'm divorced from her mom. We were co-parenting, meaning we were sharing parenting duties. So now, can anyone guess what covalent might have anything to do with? Even if you're a little bit wrong, hopefully you can get towards the right answer based on...
Like sharing?
Yes. Specifically sharing something that must involve the valence shell.
Electrons.
There you go. A covalent bond is when atoms share, basically, let's just abbreviate this for you. Atoms share electrons. One or more pair, blah, blah, blah. Yeah, that's true. Just know that if you're sharing electrons, it's a covalent bond. If you're giving them up or taking them, like we talked about previously, that's an ionic bond. So remember, sharing is covalent, and it's right there in the word. Co, like you're sharing something. Specifically, you're sharing things in that valence shell, the valence ring. Now, you do need to know that for the exam. The other thing you need to know that's very important is this little bullet point right here. It is the strongest of the bonds that we talk about. And that will be very important when we start talking about DNA. You're going to need to know, this is going to come up again later, like what is the strongest of the bonds? of the 3 bonds we talked about? And the answer is covalent bond. I'll remind you too, again, like I just said earlier, last week, this is so horrible. I wish I could do this better. Anyway, last week we talked about compounds, or I introduced you to that word. And then today I said under that category, under that word that covers a lot of stuff, you have ionic compounds, right? We talked about that. Now I'm giving you another one. Now, if we have things coming together in covalent bonds, that is called a molecule. I'm going to abbreviate because this is so hard for me to write like this, and it looks ridiculous anyway. So yeah, again, under compounds, we have ionic compounds, which we just got finished talking about, and molecules, which we're talking about right now. As far as the exam is concerned, that's probably not very important. I'm probably not going to ask you any questions. We need to differentiate between a molecule and an ionic compound. But these are just words that I'm going to use throughout the semester, so you should know them for that reason. Again, same with everything else we've talked about, the ionic compound too. We're still just trying to fill the outer shell, right? I'm going to give you some examples on the upcoming slide. But yeah, that's still the purpose. You still want the full outer shell. The only difference here between this one and an ionic compound is, again, we're sharing electrons. We're not giving up or taking electrons. And again, the next slide I'm going to show you is going to give you like a visualization. But for now, are there any questions about covalent bonds? All right. The next word, this reminded me of it, that little Hawaiian shirt thing. The next word for attendance is pineapple. All right. Here's an example. Covalent bonds. We're going to talk about carbon. Carbon's a great example because you're going to be doing that a lot in lab. The atomic number, and then again, this is just an example. There's nothing to memorize here, but the atomic number is 6. Here's something you need to know. Not specifically carbon, but if I tell you something's atomic number is 6, then based on what you do need to know for the exam, what is its proton number? How many protons does it have if its atomic number is 6?
6.
Good. 6 protons. Of course, it's also written right here. But yes, and I didn't say anything about it being charged. Therefore, it must also have 6 electrons, right? So here we go. So if it has 6 electrons, we know the inner shell holds 2. So let's see. We have 6. Take away 2. 6 minus 2 is 4. Okay, so that next shell must have 4 in it. And we know that they need a total of 8 to be filled. And it only has 4. Therefore, we know it needs 4 more to be able to have the full outer shell. Therefore, it can bond 4 times. Now, for the lab, there's a table, and it's going to be very redundant for this reason. In that table, if I remember correctly off the top of my head, the first thing I think you have to put down is the atomic number, if I remember correctly. And then the next thing it asks you for is the number of protons, if I remember correctly. And that will be redundant because the atomic number is always the number of protons. And then, if I remember correctly, it asks you for the number of electrons. And since none of those things are charged, then that, again, is going to be redundant because however many protons it has, that's how many electrons it has. Because, again, it's not an ion. It's not charged. So keep that in mind when you're doing the lab today. Anyway, any questions about this slide? Okay, again, you do not need to memorize any of this information, but this step, this logical step that I just took, steps that I just took you through, that's something you need to be able to do for the exam and for the lab. So if I give you an element and tell you what its atomic number is, that should be all you need to know to figure out everything else. From the atomic number, you should know the protons. From the protons, you should know the electrons. From that, you should know how many it has on the inner shell, and then how many it has on the outer shell. Therefore, how many more it needs on the outer shell. Therefore, how many times it can bond. Oh yeah, speaking of the table, this is the other redundant thing. These numbers will always be the same. However many electrons it needs is how many bonds it can make. Any questions about that? All right. Your book has this different picture. It's not very important, but most of the times when I draw stuff in this class and when you draw stuff, you're going to see it look like this. So I guess it's important at least once to mention the fact that there are different ways of drawing and representing molecules. So each one of these is the same thing. This is all formaldehyde, but you can see there's different ways of drawing it. And I just want you to know that because, you know, if I'm talking about an atom or a molecule and it looks like this, and I'm drawing pictures of it like this in lecture, and then you go read about it on a website, and it looks like this, you might think, what in the world? Was he wrong? But no, it's just different ways of drawing stuff. So, and then you don't need to know. I'm not going to ask you which one's the space filling model, which one's the electron configuration, which one's a ball and stick. I won't do any of that. So any questions about this? Okay. One important thing you do need to note, and this is more for your lab. This is good heads up for your lab. Double bonds, and this is the one that we're going to be dealing with. This is how you're going to draw stuff in class and in lab. Double bonds are drawn with 2 lines. Single bonds are drawn with 1 line. Also, important to note, and this is going to help you in lab. Again, you don't need to memorize this, but carbon always bonds 4 times. Now, sometimes that means, like here's an example. Carbon bonded to 4 different hydrogens. That would be methane. Not that you need to know. But look, this carbon is bonded 1, 2, 3, 4 times. Carbon always bonds 4 times. This one, and this is where it gets a little bit tricky, so I want to make sure you understand. This one has also bonded 4 times. It hasn't bonded to 4 different atoms, but it has bonded 4 times. Here we have 1, 2, 3, 4 bonds. You guys see that, right? So those double bonds, that's why it's called a double bond, because it is 2 different bonds. And that's why we have 2 lines. So if you count it, there's still 4 lines coming off of carbon. Carbon always has 4 bonds. And oxygen, for example, oxygen always has 2 bonds. But you can see here, oxygen is only bonded to that 1 carbon. But there's 2 bonds there, so it still fulfills its 2 bond rule. So any questions about that? All right. If you download the PowerPoint, you can click this little video and watch everything I've just told you, except it's animated. And that brings us to the last of the bonds that we will be talking about, which is the hydrogen bond. And this is another very important one that will come back later in the semester. First, before I can tell you exactly what a hydrogen bond is, we need a little bit of background information. First of all, you probably already know what water is, right? Water is H2O. What does H2O actually mean? That means, well, in this molecule, there's 2 hydrogen atoms and there's 1 oxygen atom. Specifically, we have the 1 oxygen atom that's bonded to a hydrogen atom here and a hydrogen atom there, right? So that's what water looks like. Here's a word you need to know that'll be important throughout the semester. And definitely to understand hydrogen bonds, you need to understand what this word is. Water is a polar molecule. It's not the only polar molecule, but off the top of my head, I think it's the only one we talk about, at least for a while. And what is a polar molecule? It is an uneven distribution of charge. Meaning, as far as we're concerned, this thing has a charge to it. Now, remember, like sodium chloride, one of them is completely positive, one of them is completely negative. Now, this molecule itself, it's not completely positive or negative because it's still the protons and the protons and electrons, they still even out. So it doesn't have a full charge. However, there's an uneven distribution of charges. Let me explain. All right. Oxygen's atomic number is 8. So what does that mean? How many all right, if its atomic number is 8, how many protons does it have? How many?
8.
Good. Yes. This thing has 8 protons. And what charge is a proton?
Positive.
Positive. Good. So just imagine, because I'm not going to draw all these because this is really hard to do. Just imagine 8 protons right here, 8 positive things right here in this oxygen. Hydrogen's atomic number is 1. So how many protons does hydrogen have?
1.
1. Good. It has 1 proton. Just that 1 plus. All right. Same with this one, right? So here we go. This thing has 1 plus. This thing has 1 plus. This thing has 8 pluses. And I'll just draw it. Why not? 1, 2, 3, 4, 5, 6. It's hard to see, but it's there. 7, 8. All right. So just ignore these. So yeah, this thing has 8 protons. Each have 1 proton. Now, protons are positive. What is attracted to protons? Like what's the opposite of plus? Basically.
Electrons.
Yeah, good. Electrons, they really like protons because Electrons are negative, protons are positive. So if you're an electron and you're hanging out here and you're being shared between an oxygen and a hydrogen, which one are you going to be more attracted to, the hydrogen or the oxygen, if you're an electron? The oxygen. Because if you're negative and oxygen's got all those positives, you're going to hang out here more often. So the electrons, it's not split right down the middle. It's not like the electrons that they're sharing are not directly in between the two. They are really, really hanging out more towards the oxygen end. And therefore, that's what makes this a polar molecule, because generally speaking, this part of the molecule has a plus charge, not a full charge, but it's partially positive, because this part has a partially negative charge because all these electrons are hanging out down here. So that's what we mean by polar molecule. So if you were to hold if you bring a water molecule to a magnet, if you had the plus side of the magnet towards the water, then the oxygen side would be attracted to it, and the hydrogens would be attracted the other way. So that's what makes it a polar molecule. Any questions on what makes water a polar molecule? You need to know that for the exam and to understand some of the upcoming concepts. So now that we know what a polar molecule is, we can talk about what a hydrogen bond is. These polar molecules result in weak attractions that are between, in this example, neighboring water molecules. But in all actuality, anytime you have neighboring polar molecules and there's an attraction between them, that's what a hydrogen bond is. But again, we're just going to focus on water for now. And this is a better picture down here of what I tried to draw earlier. Again, the hydrogen ends are slightly positive. The negative ends are the oxygen end is slightly negative because, again, this is where the electrons are trying to hang out. Therefore, when you have multiple water molecules together, that's how they are attracted to each other. The hydrogens of one molecule are attracted to the oxygens of the other, right? Because you have a plus and a negative. So that's what a hydrogen bond is. That's all because of the fact that these are polar molecules. And again, for the longest time, we're only going to use water as an example, but just in the back of your mind, or just keep it in the back of your mind that there are other polar molecules. Just water is what we talk about the most. So any questions about hydrogen bonds or polar molecules? All right. And one last time, I want to point this out again. This word slightly is very important. It's not a full charge. If it was fully charged, that would be an ionic bond, right? If you have something that's completely positive attracted to something that's completely negative, that would be an ionic bond. And it would be stronger because that would be, again, fully charged things attracted to each other. These hydrogen bonds, these are the weakest of the bonds. So know that. I thought I wrote that down on the slide, but I guess not. So remember, you need to know that covalent bonds are the strongest of the bonds. You need to know that hydrogen bonds are the weakest of the bonds. Any questions? All right. Let's talk about some chemical reactions. And we already have a little bit, so some of this is going to be slightly review. That first bullet point, nothing to know for the exam, but it's sort of like a reminder, like, okay, we're in biology. Why are we learning about chemistry? So another reminder, cells are constantly rearranging molecules. They're breaking bonds. They're taking this atom from this molecule and putting it on some other molecule, right? Constantly making new molecules, breaking bonds, forming new ones. And what we call that when this happens, when we rearrange molecules, that's just called a chemical reaction. And again, we already talked about chemical reactions earlier when I told you that it is the electrons that are pretty much what we're concerned about in chemical reactions, because we know that atoms are basically just trying to fill up their outer shell. Now, here's some stuff you need to know for the exam. And because these are just words we're going to use throughout the semester, you need to know the difference between a reactant and a product. And it's in the name. At least if you can remember, products are the end material, which makes sense, right? Like, what are you making? Oh, I'm making products. I'm producing something, right? So whatever it is you're talking about, whether it's a chemical reaction or if you're saying, milk plus chocolate, I'll even draw it out as if it was a chemical reaction. Milk plus chocolate gives you chocolate milk, right? That I would say, I might give you some goofy thing like that on the exam, and I might say, which one's the products and which one's the reactants? In this case, you're making chocolate milk, right? So in that case, that would be the product, right? As far as you're concerned in this class, and this is not always the case, but as far as we're concerned in this class, the reactants are always going to be on the left, and the products are always going to be on the right. And another thing, another rule that'll help you, as far as this class is concerned, and again, it's not always this way, but the arrow is always going to go from away from the reactants to the products. Does anybody have any questions about that? Okay. You will get an example on the exam, and you'll have to tell me which one's the reactant and which one's the product. And that's, again, how you're going to tell. In this class, it's always left to right, and the arrow always points away from the reactants to the products. Of course, in real life, and this is just for your own knowledge, sometimes reactants look like this because the reaction can go either way, but that's a whole different discussion, the one that we never even have in this course. Another thing to realize, this is important just to keep in mind, not necessarily, it might be on the exam, I don't know. When we're talking about rearranging stuff, when we're talking about these chemical reactions, it's very important to note we are only rearranging it. We haven't created or destroyed matter, right? And this is, I think this is a book example that I have down here. Here's a chemical reaction. We have 2 molecules of hydrogen peroxide. And what happens is those 2 molecules of hydrogen peroxide turn into 2 molecules of water and 2 molecules of oxygen. And if you've ever poured hydrogen peroxide on a wound or a cut or something, you probably noticed it bubbles. And what is bubbles? Bubbles is liquid and gas coming together, right? So there you go. Oxygen is the gas, water is the liquid. Anyway, the point here is, yeah, we've destroyed the hydrogen peroxide and we created water and we created oxygen, but we didn't create or destroy matter because all the matter is still accounted for. Here we have 1, 2, 3, 4 oxygens, right? And here we have 1, 2, 3, 4 oxygens. Here we have 1, 2, 3, 4 hydrogens. Here we have 1, 2, 3, 4 hydrogens. So again, we did rearrange that matter, but we didn't destroy or create anything. So any questions about chemical reactions? All right. Here's a very, very important part. Water and life. You always hear that water is important for life. And now you're going to learn about why. The next word for attendance is skate. Like if you were going to go roller skating or ice skating or that type of fish that's related to a stingray and a shark, a skate. Anyway, let's talk about water and life. Before we get into the information that you need to know for the exam, as usual, your book kind of gives you the relevance of this little section. So your book points out that life began in water. This is where it all started. It evolved. It stayed in it started in water and it stayed there for about 3 billion years before finally spreading to land. And because of that, life is still tied to water. We're basically, I don't know if I want to say it this way, but in a sense, everything's almost like aquatic. Anything that's not in the water has just evolved a way to stay out of water, right? Because we still need the water. So we've just come up with different ways of obtaining and keeping the water that we have. Here's one you should know as far as the exam is concerned. I'll go ahead and underline this. Your cells are about 70 to 95% water. I'm not big on numbers in this class, but that is a number you need to know. It is on the study guide. It will almost definitely be on the exam. So you can expect that. Cells are about 70. Your cells are about 70 to 95% water. Obviously, that depends on which cell we're talking about. Are we talking about your kidney cell, or brain cell, or eyeball cell, whatever. Depends on specifically what kind and how hydrated you are, things like that. But yeah, basically, you are mostly water, is what we're saying here. So obviously, life and water are very much connected. But the question is, why is life and water so connected, and how? And that's what we're about to talk about. So most of the things we're talking about, and you're going to need to know these things right here. There's no need to write them down right now if you don't want, because we're going to talk about them each individually. But there's 4 properties of water that are really important to life. And they are all 4 of them. Basically, it all boils down to the fact that water has this polarity and it makes these hydrogen bonds. So everything we're talking about, when I explain how it happens, it all boils down to the fact that water is polar. And again, there's no need to write that down because we're going to talk about these each individually and hopefully pretty quickly because we're running behind and this is a pretty simple concept. So the first property of water that's important that we're going to talk about is the cohesion of water. Does anybody know what cohesion means? Like if you were to say, like if you had a team, and you're like, it's a very cohesive team, right? So what do you think cohesive means? Cohesion, what does that mean?
Going together.
Good. Together being that important word there. Because water molecules stick together, right? They stick together due to their hydrogen bonding. So because of those partially positives and partially negatives of the atom, they're attracted to each other. Hence cohesion. And for your own knowledge, cohesion is when two things of the same type stick together, right? Same kind. And the opposite of that would be adhesion. So when water sticks to glass, that would be adhesion, but you don't need to know that. What you need to know is what cohesion is. And again, it's the same, two things of the same kind sticking together. And again, your book points out that it is stronger for water than most other liquids. For example, what was it? Alcohol, isopropyl alcohol. It is polar, but it doesn't have as many positive ends. It's hard to explain, but again, water has one negative and the two positives. So there's a lot of different ways it can attract. Isopropyl alcohol, for example, does not. Therefore, that's actually why it has a lower boiling point. So when you put alcohol on yourself and it feels cool, that's why. It's because it's evaporating off of you because just the heat from your skin is too much for those molecules to stay together. So technically they are boiling and they are evaporating off your skin, and that's what feels cold. Anyway, that's not important. What is important is that you know what cohesion is. And why is that important as far as life is concerned? Well, your book is the example of trees. So you might think to yourself, you might look at a tree, like a really tall tree, and think, well, I know every single cell in that plant needs water, but how does that water get from the roots all the way up to the very tippy top leaf, right? And the answer is it's the cohesion of water. And I might ask you that, I might not. But basically, I wish I could draw this. You can see here, we're zooming in, right? The water is going up. We're zooming into the inside of the plant. Here's this microscopic water conducting tubes. You might call them pipes. It's the water pipes inside the plant. But what's happening, let's assume this is the very tip top leaf. What happens is that water molecule evaporates. Boom, it's gone. It leaves the plant. It evaporates into the air. But when that thing moves forward, they all move forward. It's like a chain reaction because of the cohesion, because of that hydrogen bond. It's like a chain. It's a chain of molecules. So if you pull one up, then they all come up all the way from the tippy top to the root. Does that make sense? Okay. The next property is surface tension. And in my opinion, this one's a little bit less important as far as this semester is concerned. When we talk about how life works, we don't talk too much, maybe ever again, about surface tension. So I'm going to go through this very quickly. Surface tension is just a measure of difficulty in stretching or breaking the surface of a liquid. So, for example, this spider right here, it's not floating. It just hasn't broken the surface of the water. It is literally on top of the water. And what makes that happen? Well, like I said earlier, everything boils back down to the hydrogen bonds, right? The fact that it's polar. So because those water molecules are so attracted to each other, then it could take some weight before it breaks. Here's another picture. This is from the last Summer Olympics, I think. And it's a little bit hard to tell, but the water line is right here. So this person is above the water line, but you can see there's still water on that person because even though they broke the surface, well, they didn't break the surface. Even though they're above the water line, all that water still stuck together because of the surface tension. And again, in my opinion, this is not very important concept for this semester. So I'm just going to leave it at that. There's another picture of surface tension. I liked it because it's kind of got our mascot, and I like the shadows. The next one is how water moderates temperature. And you know what? The last word for attendance is going to be, let's call it moderation. That's the last word. And when we get back on Wednesday, this is the bullet point we'll stick with. Does anybody have any questions while we are recording?
Yeah.
Good. What you got?
What were the first two? I kind of forgot those.
I can't give those to you. But I'm sorry. Only because I don't know. I don't even know who said that. So don't tell me. So I just want you to know it's not because I don't trust you. It's just that that's how it works in general. Is that, I just don't trust anybody. So it could be that you just got on here, or maybe you were taking a nap, or whatever the case may have been when I gave the first word. So, but that is a great question, and I'm sorry I can't give it to you. But for anybody who needs those, you can watch the videos, the video once I post it. And I really am sorry. I know it's a pain, and I know if I think I know who it was, and if it was, I'm sorry. But if you weren't, I talked about that at the beginning of the classes. That I know I make it a real pain in the rear when we do online stuff instead of in person, but that's on purpose. So I am sorry. Any other questions? All right, I will be online for office hours, and then I hope to also be online for lab. So you guys go to lab if you're section 1. Go to lab today as usual, and hopefully he'll have his computer open and I'll be there. All right. So if no one has any questions, I'm gonna stop recording and log off, and then log on to the office hours.
What's the lab room number?
The lab number?
Yeah.
The one that we're starting?
No, like when I go to lab today, like what's the room number?
Oh, the room number. Thank you. Good question. It's H205.
Okay.
Wait, it's in person? The lab's in person today?
Yeah. Yeah, it'll be in person. It's, as far as you guys are concerned, nothing's changed. It's going to be like as usual. The only difference is I can't make it. So your TA is going to be in charge, and I'm going to just be there virtually.
And that's for the people who have labs on Monday?
Correct.
All right.
Great questions. Anybody else? All right. Well, again, I'm going to log off here. I'm going to stop recording. I'm going to log off, and then I'm going to log right back on to the office hours. So if you need me, I'll see you there.